as it says here. So now for some hot stuff. Here's a really nice image of some lava. You can say that it's hot from Pahoehoe, that is in a big island in Hawaii, one of the islands, actually the big one, the one that actually has the telescopes on the top of it. We're going to talk about that in the next chapter. So anyway, here is the message that we're going to talk about today. The important thing is that light intensity, and you might figure it out that the light that is emitted by this lava, right? So lava emits light. All right, okay. And the intensity and color, they actually relate to the temperature, right? So they relate to how hot the object that emits the light is. So this is one example, right, of what the scientists call blackbody. What is a blackbody? Anything that has a temperature, right? So blackbody, anything has a temperature. So that can be you, that can be this hot lava, and that can be your chair, that can be anything, right? So you can pretty much see that this is hotter and this is colder, although I wouldn't call it cold because you can actually get burned on that black looking lava. So you see the colors are different, and you can tell by their colors which one radiation, that is the type of light that is emitted, okay, is more intense. All right, so again, light is thermal radiation, right? So this is what we find out here. Some of the properties, intensity and the color that relates to the temperature of light that is emitted by pretty much anything. And by the anything, we're going to call that anything also a blackbody. So it was over the 19th century, starting with actually the beginning of the 19th century, scientists were exploring the properties of the heat, and it was discovered that all objects emit heat radiation, and that the intensity and its color depend on the temperature. All right, examples of heat radiation, these are examples of blackbodies. So for example, I don't know, could be you, cat, snake, right? Maybe different temperatures, but not that much different. We're around 300 Kelvin, okay? So that is the temperature that you can measure with your thermometer, although you measure temperature in Fahrenheit, right? But you can also measure it in Celsius if you were to live somewhere, pretty much anywhere outside the US, right? But any one of those can be converted into Kelvin, which is the standard unit for temperature. And it's important because all the scientists use it, and it's important that all the scientists use the same units so they can actually understand one another, learn from one another, and so on. All right, so at this temperature, that blackbody of ours, or of our dog if you want, glows, that is, it emits, right? Emits radiation which falls into the infrared part of the electromagnetic spectrum. And so the wavelength of the radiation that you emit, that is around 10 micrometers or microns. All right, so that's what you do. You're glowing with a 10 microns light. All right. Also, don't confuse that with what you're seeing by looking at your dog or your cat or your fish or your friend. That is the scattered light, which is obviously coming from the sun or from a source of light. That is scattered light, right? This is what you see. Obviously, the 10 micron, you don't see with your eyes. You would need some infrared glasses for that, right? Because that is, again, that is emitted in the infrared. But as you move towards hotter, right? So this would be a hotter blackbody, the furnace. Okay, so that's hotter. That intensity moves towards near infrared. So basically at the red, very red edge of the visible range of what our eye can see, right? And the wavelength associated with that light as the wavelength is 3 microns, all right? Okay, so because there is some light that is emitted in the red, you get to see it as red. Now, even hotter, it's going to be the sun and some other stars, right? And we're actually talking about the surface of stars. The interiors of the stars are much, much hotter than that. So the surface emits in visible. We call it visible or optical. That's the light that our eyes are sensitive to. Right? So this is the sun. These are other stars. These are actually stars in a group of stars. That is called the Pleiades. Or the Seven Sisters, or Subaru. You've heard about those. They're blue, as you can see. Okay, that means they are hotter, much hotter than the sun, which is red. Is red because of the exact wavelength at which that maximum intensity is. That's how we see it, right? Okay. So basically the conclusion or the message you need to take out of this is that an object, any object's thermal radiation spectrum depends on only one property, which is its temperature. Okay, so let's talk a little bit about that. Okay, there are some very important properties that I'd like to discuss with you. So here are 3 examples of stars. At different temperatures, right? So this is 15,000 Kelvin. This is about 6,000 Kelvin, and that's the temperature of the sun. And this is a cooler star, and this would be a hotter star. And this is just the sun, somewhere a medium temperature star. Okay, so we have the curves in 3 colors: the blue for the hot star, the yellow for the sun, and the red for the cooler one. right? Here's what we have on the y-axis, right? This is the intensity per square meter of surface, right? What is intensity? Intensity is energy per time, that is power, and also per unit area, okay? And that is important because it allows comparisons of things, objects, stars of different sizes, right? So we are only looking per unit area per meter square, how much light, right? So this is how intense is light per each meter square, okay? We have as a function of wavelength, and that is here in nanometers, okay? Remember, nano, that is 10 to the minus 9 meters. So anyway, right, so we have 3 stars, and you can see there is a characteristic shape that's also called the blackbody characteristic shape. So every time you see something like this, intensity as function of wavelength for any blackbody is going to look like this. So there is a maximum, right? This is basically where intensity is maximum. Well, that maximum corresponds to a certain wavelength, which is not a maximum wavelength, is the wavelength at which the intensity is maximum. So you can see for this star, the cool star of 3000 Kelvin, the maximum seems to be about here, okay? How about the hot star, the hottest star, right? So the maximum, you see it moves, right? It happens at shorter wavelength or higher frequency. Let's use F, or higher energy, right? So the light, the maximum of the light that is emitted by a hotter star is shorter wavelength, therefore bluer than the one wavelength at which the maximum happens for a cooler star, right? So this is longer wavelength. So that is rule number 1, or property number 1. Hotter objects emit photons with a higher average energy or frequency. And we can add or. If it's higher average energy, it's going to be shorter wavelength. Okay, so that's rule number 1. We're also going to meet it as Wien's law, because Wien was the scientist who was able to quantify this. The other law is obviously the one number 2. It says the hotter objects emit overall more light at all frequencies, right? That's what I meant by overall. More light at all frequencies per unit area. As you can see, this is the red curve, right? You see it's always lower at all these wavelengths. You look at the intensity, right? At all wavelengths is a lot less than, right? Look at the same frequency. What happens to the really hot star? Much more intense. Much more intense at all wavelengths. All right. This is Stefan-Boltzmann law. So we have 2 laws. Let's see if we can apply them discuss actually in a little bit more detail about them. So you're going to apply them. We're going to understand how useful they are for us to characterize the things that you observe in the sky. So Wien's law, that was law number 1, that said, oh my, I'm going to write this again. And this is wavelength, right? Lambda max. So lambda max, okay, or the wavelength at maximum intensity is related to the temperature T of that object, okay, by this relation. It is 0.0029 Kelvin times meter divided by temperature in Kelvin. So forget about this one. This is the formula that we are going to use, right? So even if the temperature is given to you in a problem in either Fahrenheit or Celsius, make sure you have that in Kelvin units. All right, so of course you can imagine you're going to have Kelvin here, they're going to cancel, and so the final answer will be in meters. So you might need to convert to nanometers or micrometers or millimeters or so on, right? Just to have an easier to read number. All right, because meters for wavelength, that's usually going to be, kind of far radio. They're very useful. It's just, in the X-rays, it's going to be 10 to the minus 10 meters or an angstrom, something like that, right? Okay, so why is this useful? Okay, remember that peak wavelength, right, or lambda max, the wavelength at the peak intensity, actually that corresponds to the color of the object, right? Because that's going to tell, hey, it's that wavelength that the intensity is the lightest, okay? And the color is the wavelength, actually. All right, and so if we compare objects of different colors, then the bluer one is always going to be the hotter, right? So this one, not much color. That means it's pretty cold, right? All that red actually turned into black given how cold that is. It's not hot enough. And then it becomes red, and then it moves towards a mix of red and blue, but more and more blue for hotter and hotter, if hotter and hotter, right? So that's why it's gonna look like a white one. All right, so that's all there is, right? So basically, the larger this number, the temperature, the smaller the wavelength will be. So hotter, that is large number for T, is going to be a small number for lambda, so a shorter wavelength or higher frequency or higher energy. Okay, you can always pause these kind of lectures and read again, or maybe just listen to all these explanations again and again if needed. There's always the homework on mastering astronomy that is going to emphasize these things more. All right, so the second property, if you remember, I said Stefan-Boltzmann law for a black body. Again, anything with a temperature. That can be you, that can be a star, that can be the whole Earth, right? Anything. For anything with a temperature, you're gonna apply that Wien's law, and now we have the second law that refers to the total energy given off by that body, black body, but by that system or object, okay? Well, that is again linked with the temperature, and basically this is the formula. So here's what we have. It's called F, you can call it I total or total intensity. Okay, which is again total energy per unit time per area. All right. Okay, so all that energy is basically proportional to the fourth power of temperature. And then we have this sigma, another Greek letter, that is the Stefan-Boltzmann's constant. That is a constant. So that is actually having the same value for all objects, regardless of their temperatures or anything. And the units now ended up kind of funky. So here's the real unit. So we have watts, which are actually joules per second, because it comes from power, which is energy per time. And remember the units for energy, they're joules. All right, so we have watts per, that's why you have power of 2, meter to the -2, and then Kelvin to the -4. So there's another way of writing it. So we have sigma is 5.67 times, again this is -8 here, right? 10 to the -8, and we have watts per meter squared per Kelvin to the 4. Remember, 1 over, say, x to the a is x to the power of -a. Just a parenthesis here to remind yourselves how to play or manipulate the powers. All right, let's apply all these things. So let's look at this problem. Very similar to, I'm hoping, what you're going to find on Mastering Astronomy website, the homework. So the question is, which one is hotter of the following? A, B, C, a blue star, a red star, or a planet that emits only infrared light, or actually its maximum intensity is in infrared light. Okay, so basically we're seeing a blue that is shorter wavelength, okay, because it's the blue end of visible, and then we have longer wavelength because it's the red end of the visible spectrum, remember? So we have visible here, and if the wavelength increases this way, then this is red, this is blue, here would be ultraviolet, and here would be infrared. So this is where you would expect to see that lambda max in infrared. So that means even longer than red. Okay, so that we know can translate into the temperature, right? So that now we have, we're gonna use Wien's law, right? Let's remind ourselves what that is. This says lambda max is 0.0029 Kelvin times meter divided by the temperature in Kelvin. So basically, if this is smaller, and this would be larger. So which one is the hottest? We need to look for the situation in which we want this to be a high number, okay? And so lambda max needs to be the shortest. So this would be the hottest, right? So T highest. Okay, T lower. And so in this case, in infrared, T even lower. So if you were to put an axis here to correspond to the wavelength, the temperature would increase this way. So we have hotter things here and colder things here, right? So infrared, and then you go to radio, right? Radio emitting things are the coldest things, and then you move towards hotter things. Then you have X-ray, this is pretty hot, and then the gamma ray emitters, even hotter, even more energetic things. Yeah, so this is the line of thought that you should have when you answer questions like this. How about this question? We have a star that is assuming to behave like a blackbody. Actually, most of the stars, as we will see, behave very much like a blackbody, especially even our sun. So now, if the temperature of that star doubles, so you go from T to 2 times the temperature, then what can you say about the wavelength at the maximum intensity? Will be how many times the original wavelength? And we have here some options. Now we can guess, or we can actually, we're going to use Wien's law again. So let's write down the law. Lambda max is 0.0029, some units here, Kelvin times meter divided by temperature, right? So if this was initial, and then the temperature becomes twice, then the new wavelength max is going to be 0.0029. These things don't change. And then we have 2 times the temperature, right? Okay, so we can rewrite this. It's going to be 1/2 of, basically what's left here is going to be 0.0029 divided by 10, which is initial lambda max. So we found the ratio, okay? The correct answer will be half, right? The new wavelength at maximum intensity will be half, or 0.5 times the original wavelength. And here's another example where you probably guessed we're going to apply Stefan-Boltzmann's law. Remember, the flux or the total intensity is sigma times temperature to the 4th. So this is the law we're going to use. Now let's read the question. Should have done that before. So a star is assumed to behave like a blackbody, and as I said, that happens actually very much with almost all of the stars that we see out there. Now, if the temperature of that star doubles, so again, we're in that situation, 2 times the temperature, right? So initial, and then new temperature. All right, what's going to happen with the flux? All right, so the new flux or total intensity is going to be F prime, is going to be sigma, the same, right? This is just a constant. It's Boltzmann's constant. And then we have the new temperature. Remember, that is 2 times the old temperature. Everything to the power of 4. All right. So now this can be written as 2 to the 4 times t to the 4. Now you can calculate that. This is 2 times 2 times 2 times 2. So that's 4 times 4, I think that is 16, right? Because the multiplication is commutative, it doesn't matter in which order we're pursuing that multiplication. Then I can take this 16 factor or this one out. So it's going to be 16 times sigma T to the 4. And I can group them, and here's what I find. This is the flux, the initial. So, what do you think? The new total intensity will be how many times the original one, right? So the temperature at the start doubles. The new intensity is going to be 16 times higher than the original one. And we just proved it here. So that's about it for now.